Wildland fire can shift and erupt in an instant. It is essential for the wildland firefighter to recognize and react quickly when facing changing environmental conditions which impact the fire behavior of the incident. Failure to recognize critical fire behavior conditions could place your crew and yourself in a deadly situation. Understanding the tactics for controlling the spread of wildfire is essential for the wildland firefighter. However, using the knowledge and understanding of fire behavior may someday save your life. In Part 1 of this course, we discuss the chemistry of fire and the first two environmental factors that influence fire behavior, topography and fuels. In this segment, we will discuss the third environmental factor, weather, and review examples of extreme fire behavior conditions and how we can predict fire behavior. Weather influences a significant part of how a fire behaves. There are three factors which affect the start and spread of fire: temperature, wind, and relative humidity. In order to predict fire behavior, we must be able to observe the present conditions of the fire and research both the past and future weather reports in an attempt to predict current fire movement. Air temperature and its corresponding moisture content directly affects how a fire will burn. As hot air draws moisture from dead fuels, it dries the fuel further, lowering ignition temperatures. Air temperature is affected indirectly by solar radiation. As solar radiation warms the earth, it changes the temperature of the fuels. The rise in temperature of the fuels changes the air temperature. Air temperature can also have an effect on firefighters. The hotter the temperature, the more safety precautions need to be taken. To avoid heat-related hazards, firefighters should drink plenty of fluids and avoid fatigue. One of the most significant environmental influences on the spread of a wildland fire is wind. Wind is a natural force which can drive fire, making it very unpredictable. The force of wind can impact the direction, spread, and behavior of fire. In general, the stronger the wind, the faster the spread of fire. Wind is the primary factor that influences fire spread. Wind brings an additional supply of air to the fire that can cause it to react violently. As it blows, wind pushes and bends the flame closer to the ground, which preheats the fuels ahead of the fire, taking vital moisture from the fuel. This condition creates a wind-driven tinderbox. Wind creates spot fires by blowing sparks and embers out ahead of the fire and into unburned fuels. As wind blows over topography, it creates additional problems by causing the air to become very erratic. As wind crosses intersections of ridges or canyons, it creates swirling eddies which form whirlwinds and dust devils. Wind can also pick up speed as it pushes along valleys and funnels up through canyons. In both situations, topography is at the root of the unstable air movement, creating extreme and unpredictable fire behavior. Always be aware of the topography within the region you are working. It is important to understand the potential effects it might have on the wind. Incoming weather fronts can also bring dangerous wind changes. The passage of these fronts usually accompanies a shift in wind direction. It is not uncommon for warm fronts to shift the wind direction 45 to 90 degrees. Cold fronts have the potential to shift wind direction as much as 45 to 180 degrees. This erratic wind shift can turn the head of a fire around and move it in the opposite direction. Large, well-developed fires can create their own weather patterns. As fire burns, it develops thermal air currents which can affect the prevailing wind, increasing the spread of fire. The air above the flames quickly rises and becomes superheated. This pulls fresh air in from the ground and sides, making the fire burn hotter and more intensely. Winds tend to build throughout the day. The calmest times are between 4 and 7 a.m. During the morning hours, solar radiation warms the ground in lower elevations. This heating effect warms the air just above the ground, creating slope and valley winds. As the low-lying air heats up, air currents begin to flow uphill through the canyons and slopes during the day. In the evening, when the high air currents begin to cool, they reverse direction and begin to flow back down the canyons and slopes to lower elevations. It is important to always consider the direction of canyon and slope wind flow when planning an attack on a fire. Unique conditions are always possible, and it is important to remember there can always be variations in weather patterns throughout any fire. The temperature of the wind also influences fire behavior. Generally, the warmer the wind, the fiercer the fire. Hot, dry air draws moisture from the fuels and preheats them, generating quicker fuel ignition and hotter fires. Cooler air can have a higher moisture content, which dampens fuels and slows their ignition and spread. These factors make the wind temperature important when attempting to predict fire behavior. There are several different wind types which can impact fire behavior and spread. One type of wind is called a feign wind. A feign wind is also referred to as a gravity wind. This wind occurs when air spills over high elevations and moves down into valleys. A feign wind can also occur when a high-pressure system locates itself in and around mountain ranges. Airflow around the high-pressure system causes some air to spill over the higher elevations, creating a strong downhill wind moving at a high rate of speed. As a feign wind flows downslope, it compresses into the atmosphere and becomes warmer and much drier. This drying effect begins to dry out fuels ahead of the fire, increasing both temperature and wind. These increased temperatures can force wind gusts in excess of 50 to 70 miles an hour. Some of the largest, most damaging, and most costly fires in the West were fueled by gravity or feign winds. Some winds occur so frequently that they have earned reputations and have been given their own local names like Santa Ana, Chinook, and Sundowner. The air always contains some amount of moisture in the form of water vapor, which is the measurement known as relative humidity. Relative humidity is an important measurement because of its effect on fuel moisture. The definition of relative humidity is the ratio of the amount of moisture in the air to the amount which the air could hold in the same conditions if it were saturated. In this case, as the temperature rises, the relative humidity level will drop, causing the fuels to become drier. On the other hand, as temperature decreases, the air vapor gains moisture, causing the relative humidity level to rise. Relative humidity is most important as a fire weather factor in the air layer nearest the ground. It is in this layer that relative humidity can directly affect both fuels and fire behavior. If relative humidity drops below 30%, fire can burn freely. If it drops below 10%, fire danger is critical and extreme fire behavior is possible. Relative humidity is affected by several variations such as season, time of day, slope, aspect, elevation, and vegetation. Relative humidity directly affects the amount of moisture in the fuel. As air receives moisture from wet fuels, dry fuels receive moisture from the air. The moisture content of fuel is an important factor in firefighting. Wet, live, or green fuels do not burn freely, but the drier the fuel, the easier it ignites and burns. Firefighters working nighttime operations can look forward to wetter fuels, winds, and lower temperatures. Nighttime air is usually higher in moisture content than it is during the day. As the lighter fuels absorb moisture from the cooler night air, they burn at a slower rate. This explains why fire that resists suppression during the day can sometimes be suppressed more easily after dark. As both relative humidity and fuel moisture content levels drop during the day, firefighting efforts may become ineffective. If a fire is difficult to control during the day, an all-out effort must be made at night. Understanding the relationship between relative humidity and fuel moisture content becomes a critical factor as it affects wildland fire behavior. Air stability is the fourth weather factor that influences fire behavior. Air stability may either encourage or suppress vertical air motion. Although vertical air motion is less obvious than wind, its effects are equally important on fire behavior. Stable air has little vertical air movement, but if the air is unstable, it may be prone to updrafts. Updrafts draw their air in from the sides, creating turbulent, gusty winds which can cause erratic fire behavior. Thunderstorms also tend to develop in unstable air. Their strong updrafts and downdrafts could cause lightning and strong surface winds that create dangerous conditions on a wildland fire. Air stability in a thunderstorm can become quite unstable. If the thunderstorm column collapses, air can suddenly be released downward. This strong downward movement of air is called a downburst. A downburst is a phenomenon involving significant downward vertical air movement. When this cool column of air strikes the surface, it spreads in all directions like water poured from a pitcher, causing havoc if it occurs over a fire. Downbursts strike suddenly and violently, but last only for a short period of time. Dust devils, mirages, and fire whirls are indicators of unstable surface air conditions. They are indicators of possible erratic fire behavior. These indicators are usually the result of uneven ground temperatures. Dust devils and fire whirls happen when unstable air moves across uneven surface temperatures. An inversion is a warmer layer of air on top of a cooler layer. These stable layers can have major effects on a wildland fire. For example, if an inversion sits above a wildland fire, the low, cool air will cool the surface fuels. These lowered fuel temperatures keep the fire burning at a lower intensity. A fire covering several thousand feet in elevation can burn differently on either side of an inversion. In the warm, dry air above the layer, the fire will burn with great intensity even at night. The portion of the fire below the inversion will die down and may calm the fire behavior.
I have a dry bulb of 79, wet 57, RH 25, winds out of the west 4 to 7 with gusts.
But if the fire grows to where the heat column pushes through and destroys the inversion layer, cooler air rushes in to replace the heated air, causing very erratic fire behavior. The behavior of a fire burning under an inversion may change abruptly when the layer is destroyed. When an inversion begins to break or lift, the air mass loses its stability. The winds resulting from this unstable condition can intensify fire behavior. Inversion layers can break up when wind mixes the stable air. They also dissipate when solar radiation heats and lifts the layers, usually at about the same time each day. Inversions also present visibility problems. An inversion prevents smoke from rising away from a fire, trapping it low to the ground. This smoke can create hazardous conditions for aircraft trying to fight the fire. Inversions are common along coastlines and in mountains during the morning hours. Cloud cover is our last weather factor that has an influence on fire behavior. A change in the visible cloud cover may indicate a change in the local weather pattern. For example, a line of cumulus clouds approaching from the west or northwest can be an indicator of a cold front passage. Large clouds of dust can precede the arrival of a cold front. Winds will become strong, erratic, and gusty as the front reaches your location. A potentially dangerous situation caused by passing cold fronts is an abrupt change in the wind direction. Strong southerly winds ahead of the front can drive the fire ahead to the north or northeast. Winds shifting to the west or northwest after the front passes can drive the fire ahead to the east or southeast. Passing cold fronts can also bring a rapid drop in the relative humidity within 24 hours of passage. Another example of cloud cover affecting the weather pattern is a tall building cumulus cloud with a dark, flat base and precipitation falling out of the bottom. These tall clouds may be an indication of a developing thunderstorm, which can bring gusty surface winds or create downbursts which can affect the fire's direction and intensity. A thunderstorm's winds will often be 25 to 35 miles an hour and can reach as high as 60 miles an hour. Thunderstorms also produce lightning, which is dangerous and can ignite additional spot fires. A second important way clouds can influence fire behavior is by affecting the temperature of fuels. Fuels under the cover of a cloud will not be heated by the sun's radiant energy. Cold fuels are fuels under a cloud cover. They stay cooler and ignite and burn more slowly than hot fuels heated by solar radiation. Wildland fire can sometimes erupt into extreme fire behavior conditions.
Apparently we're starting to get some spotting. I'd like to pull those tenders now if I can.
These special conditions include area ignition, crowning, and other extreme fire behavior. Area ignition most often occurs in steep, narrow canyons or box canyons where winds commonly saturate an area with spot fires. The radiant heat from the individual spot fires causes them to affect each other, heating all the unburned ground fuels between them. Eventually, the spot fires burn together to ignite large areas in a very short time. Area ignition fires can consume hundreds of acres in a matter of minutes. Crown fires are another example of extreme fire behavior. Crown fire occurs when convective heat carries a surface fire up into the unburned upper portions of brush or trees and burns along their tops. To make the leap into tree crowns, a crown fire must have ground fuels tall enough to move a ground fire up into upper tree limbs. A crown fire also needs to have tree crowns dense and continuous enough to spread the fire. This crown fire ignition and spread can happen incredibly fast. Crown fire's capabilities to spread quickly makes it especially dangerous to firefighters. Ground fires can present a second danger in an already burned area. If a ground fire moves through an area without burning the crowns, a reburn in the form of a crown fire is still a possibility. When it happens, the crown fire may actually burn with much more intensity because both radiant and convective heat from the first fire has dried and scorched the aerial fuels above. Extreme fire behavior is also known as a blow-up situation. Extreme fire behavior can be expected when all of the various factors that affect fire are at their worst. There are many indicators of extreme fire behavior. If the fire rapidly increases in intensity or spreads at a high sustained rate, has a well-developed convection column, is throwing spot fires out over long distances, generates fire whirlwinds or horizontal sheets of flame, or the wind suddenly calms and could shift, the fire has reached a point where conventional firefighting methods will have little effect. A blow-up situation makes direct attack and control of a fire impossible. The fire's intensity and rate of spread will defy any suppression efforts. Firefighters must determine when a change in weather, fuels, or topography will reduce the fire's intensity and allow them to resume. Until firefighters can reestablish operations on the main fire, they can continue to work on safe portions of the fire line. Firefighters should take all the safe preventative actions they can to protect property and resources that might become involved in the fire. Firefighters can predict fire behavior, but fire prediction is not an exact science. Fire prediction requires practice and experience. Firefighters must predict the fire as they fight it. The goal of safe wildland firefighting strategy is to match the firefighting tactics to the anticipated fire behavior. If the fire behavior prediction exceeds the tactic must be adjusted before the situation becomes dangerous. Every firefighter must recognize what's happening in their surroundings and know how to react properly to each situation. Predicting fire behavior begins with understanding the weather and how it influences fire. The following examples are all fire behavior indicators. It is important to understand what they mean. A leaning smoke column indicates a rapid rate of fire spread and short-range spotting. A sheared smoke column means winds aloft may cause long-range spotting. A well-developed smoke column means intense burning and unpredictable fire spread may occur in any direction. A smoke column that is changing to a darker color, beginning to rotate faster or split, can indicate the fire is increasing in intensity. A fire that has enough power to become stronger than the power of the wind is called a plume-dominated fire. The danger of a plume-dominated fire is the potential for downbursts. A smoldering fire that is picking up means your weather factors are changing. Firefighters can anticipate an increase in the fire's intensity. Torching trees are an indicator that a fire is starting to transition from a surface fire to a crown fire. Fire whirls are another indicator that a fire has the potential to move from a surface fire to a crown fire. Fire whirls can pick up large burning embers and throw them far across the fire line, causing numerous spot fires. Frequent spot fires have the potential to increase the fire's spread and complexity. During this course, we have discussed fire weather and the indicators associated with approaching weather fronts. We have discussed the 3 feign wind conditions associated with weather fronts and have discussed the specific hazards connected with thunderstorms. We have discussed wind cycles and the impact they have on fire on slopes and valleys, and we have discussed environmental indicators that can produce extreme fire behavior. Understanding fire behavior is critical to your survival within the wildland fire environment. Your ability to anticipate and recognize potentially dangerous situations could someday save your life. During the next segment of the Essentials of Wildland Firefighting, we will be discussing fireline safety and the hazards commonly associated with fireline activities.